Bismillahirrahmanirrahim. In today's quantum mechanics lecture, we are going to again revise the topic of operators, and we will extend it where we left it in the previous lecture. Actually, this is a very important topic in quantum mechanics, the concept of operators, because whenever we start a problem in quantum mechanics, we start from the operators. Just like dynamical variables in classical physics, because you know well about the classical physics, that there are much importance of the uh, dynamical variables like position, momentum, kinetic energy, each and everything. And whenever we start a problem using Newtonian mechanics, we always talk about the kinetic energy, potential energy, total energy, momentum, angular momentum, etc. We we always calculate such variables, and from these variables we define different properties of the classical objects. Similarly, in quantum mechanics, we always talk about operators. For each dynamical variable, uh, there is always a operator corresponding. So, in previous lecture, I defined the different, operators and their basics, and now I am going to tell you about these operators in more detail. As you know, whenever we apply the operator on a cat, it will transform the cat into another cat. Just like this, a operator when operates on psi, it transforms into another cat, psi prime, and similarly like draw. Uh, and we discussed about different properties of these operators. I will not discuss them again because you know. But the important thing is about the linear operators. These are very important because we have to use all these operators in the next chapter and in defining the um, postulates of the quantum mechanics. Linear operators are those operators which distribute themselves for different cats, for different states, for different, parts of the state. The state may have different further substates. For example, you have a wave function psi. It may be the combination of two substates psi 1 and psi 2 with the multiplication of some scalar values. Like in this situation, we have a state like this, as I have highlighted in the text. You may see that this whole thing is a wave function psi, and this is a linear combination of psi 1 and psi 2. Psi 1 and psi 2 are, you can say, substates of a particular system, and they are linearly combined. Why linearly? Because their coefficients have power 1. A1 have power 1, A2 have power 1. Then there might be some condition in which the coefficients will be A1 square or A2 square, like this. Then that will not be a linear combination. This is a linear combination, that two substrates are joined with each other with the multiplication of some scalars. So this is actually the whole state psi. When I operate A on this psi, then this A operator distributes itself on the substate psi 1 and substate psi 2. So A is distributed here. So this is called the linearity of an operator. That operator distributes itself in a linear way to the each substate psi 1 and psi 2, and if you have further states psi 3, psi 4, then E operator will operate on each substate in a sequence. So that is a linear operator. ये बहुत इंपॉर्टेंट ऑपरेटर है आपके लिए, इसको हमने फर्दर आगे यूज भी करना है। और अगर हम इसकी एक्सपेक्टेशन वैल्यू डिफाइन करें, एक्सपेक्टेशन वैल्यू इज जस्ट एवरेज वैल्यू इन क्लासिकल फिजिक्स, because while we take data in classical physics, you often use that this is the average value. For example, you define the position of some particle in the y-axis. Let's say this is the origin and this is the y-axis. So if you find its length in a single step, this will not be much accurate. And if you calculate its length in 2 or 3 ways, and then you take the average, that is more appropriate. Similarly, in quantum mechanics, whenever you want to take the value of an operator, you often use the expectation value or average value. And how to calculate that average value? You calculate average value as in we did it in chapter 1, I think. This is equal to average value of, let's say, operator x is integral psi steric x operator and psi into dx. This is called average value in which operator is sandwiched between the complex conjugate and the wave function itself. Uh, so, uh, but now we are using bracket notations. In bracket notations, we did it like this: A average is equal to, this is bra, which is psi steric, then operator is sandwiched, and then the cat. This is the bracket notation. You know, this represents psi steric, A operator, and psi. So again here, operator is sandwiched between the psi steric and psi. In other words, you can say operator is sandwiched between bra and cat, and divided by the normalization condition. Normalization condition, if the wave function is normalized, then psi bra psi cat is equal to 1, because psi steric into psi is equal to 1 whenever the wave function is normalized. So for the precautionary measure, we write it here: if the wave function is not normalized other than equal to 1, then it will be divided. If it is equal to 1, then it is meaningless to divide it. So this is called the average value, or expectation value is defined like this. Okay, the important operators we are now going to define. But before defining that operators, we will define Hermitian adjoint. Actually, we want to define Hermitian operator and skew Hermitian operator, or non-Hermitian operators, which are very important. But to define a Hermitian operator, we just have to know about Hermitian adjoint. Then we will be in a position to define the Hermitian operator. That are very important operators, and in quantum mechanics, because energy operator, which is Hamiltonian, that is a Hermitian operator, and then position operator is a Hermitian operator, potential energy operator is a Hermitian operator, but we should know what are the Hermitian operators in real. So first of all, we will define Hermitian adjoint, and then we will use this definition for the Hermitian and skew Hermitian operators. Hermitian adjoint or conjugate, if we take it for a complex number, it is just the complex conjugate of a number. For example, we take a dagger. We represent Hermitian adjoint by a sign dagger. This sign is called dagger sign, like just like a sword. This is a dagger sign. So a dagger is some complex number. A dagger or a Hermitian adjoint. Hermitian adjoint is represented by the sign dagger. And a dagger is of a complex number, is the complex conjugate of that number. It means a dagger is equal to a steric. For example, you have a complex number iota, its Hermitian adjoint will be minus iota, because A steric is equal to minus iota steric is equal to minus iota. Just like a complex number. If you have a complex number, for example, 5 iota plus 3, its dagger will be equal to minus 5 iota plus 3. Just like you take the complex conjugate of a number. That is very simple. And then we define the Hermitian adjoint of an operator. This was the Hermitian adjoint of a complex number, simple. Now, how to define the Hermitian adjoint of an operator? Let's say we have an operator A, and its Hermitian adjoint is defined as A dagger into psi bra into phi cat. This is the average value of psi and phi. There is a common region between psi and phi states, and we take the average value of that region. And how we take dagger of that average value, that expectation value, Hermitian adjoint, we will actually take the complex conjugate of whole this average value. We take the average value A, and then now you can see that cat is converted into bra, and bra is converted into cat. Please listen carefully this point. Again, I repeat that A dagger here is psi bra and phi cat, but on the right hand side you see that here is phi bra, because the cat of this side is now converted into bra. Hermitian or adjoint always transforms a cat into a bra and a bra into cat, a real number into its complex conjugate, or a complex number into its complex conjugate. So from here you can see that A dagger psi bra phi cat is equal to now phi bra and psi cat. Phi and psi are interchanged in this situation. Means cat is converted into bra and bra is converted into cat, and this average value and the whole steric. This is defined as Hermitian, you can say, adjoint of an operator. So I summarize that Hermitian adjoint of the complex number is equal to complex conjugate of that thing, and Hermitian adjoint of an operator is equal to this equation, in which psi is converted into cat, is converted into bra, and bra is converted into cat, and we take the complex conjugate. So this is the definition of Hermitian adjoint. I once again repeat its different points, different properties. First of all, if you have a combination of complex numbers and operators, then what steps you will do to take the Hermitian adjoint of that system? First of all, you will do that, you will replace the constants by their complex conjugates. Whatever the constants are, whether they are real, whether they are complex, you just replace that constants with the their complex conjugates. If you have 5, let's suppose a scalar, you will replace it 5 steric, and 5 steric is equal to 5. So that is simple. Then if you have a complex number, let's suppose iota, you will replace it by minus iota, which is the complex conjugate of this thing. And then replace cats by corresponding bras. कैट्स को आपने ब्राज में चेंज करना है, और ब्राज को आपने किस में चेंज करना है, कैट्स में चेंज करना है. कैट और ब्रा जो है वो आपस में क्या हो जाएंगे, रिप्लेस हो जाएंगे. पहले नंबर पे आप किसी भी कांस्टेंट को उसके कॉम्प्लेक्स कंजुगेट से चेंज करेंगे, आप किसी भी कैट को ब्रा में चेंज करेंगे, किसी भी ब्रा को कैट में चेंज करेंगे. और ऑपरेटर्स को किस में चेंज करेंगे, ऑपरेटर्स को आप उनके हर्मिशियन एडजॉइंट्स में चेंज करेंगे। हर्मिशियन एडजॉइंट्स में कैसे चेंज करेंगे? हर्मिशियन एडजॉइंट में हम इस इक्वेशन की मदद से चेंज करेंगे। दिस इज द डेफिनेशन ऑफ हर्मिशियन एडजॉइंट। सो 3 स्टेप आपने करने। कोई भी कांस्टेंट हो उसको कॉम्प्लेक्स कॉन्जुगेट से चेंज करना है। कोई भी आपके पास कैट हो उसको ब्रा में चेंज कर देना है, ब्रा हो तो उसको कैट में चेंज कर देना है। अगर आपके पास ऑपरेटर हो उनको हर्मिशियन एडजॉइंट में चेंज कर देना है। दैट इज अ सिंपल वे to take the Hermitian conjugate of a complex system. अब इसकी कुछ प्रॉपर्टीज हैं वो देख लेते हैं। अगर आपके पास 2 दफा किसी ऑपरेटर का डैगर लेते हैं, जिस तरीके से अगर किसी कॉम्प्लेक्स डिजिट का आप 2 दफा कॉम्प्लेक्स कॉन्जुगेट ले लें तो वापस वही डिजिट बन जाता है। फॉर एग्जांपल आयोटा कॉम्प्लेक्स कॉन्जुगेट लेंगे माइनस आयोटा, अब माइनस आयोटा का अगेन कॉम्प्लेक्स कॉन्जुगेट ले लें तो वो वापस क्या बन जाता है? आयोटा बन जाता है। तो 2 दफा किसी भी कॉम्प्लेक्स नंबर का अगर आप कॉन्जुगेट लेंगे तो वो वापस वही डिजिट बन जाता है। डबल कॉन्जुगेट ऑफ अ कॉम्प्लेक्स नंबर इज इक्वल टू द डिजिट इटसेल्फ। यही रूल यहाँ पर भी अप्लाई हो रहा है दैट व्हेन वी टेक double conjugate, double you know adjoint of a operator, it will give you the operator itself. A double dagger, a dagger and then dagger is equal to a. इसी तरीके से अगर आपके पास कोई कॉम्प्लेक्स नंबर a है और उसके साथ कैपिटल A ऑपरेटर मल्टीप्लाई हो रहा है, तो आप देखेंगे कि ये जो कॉम्प्लेक्स नंबर a है वो किस में चेंज हो रहा है? कॉम्प्लेक्स कॉन्जुगेट में चेंज हो रहा है। और जो आपके पास कैपिटल ए ऑपरेटर है वो किस में चेंज हो रहा है? डैगर में चेंज हो रहा है। तो यही बात तो हम लोगों ने पीछे की है। इसी तरीके से अगर कोई ऑपरेटर पावर एन हो और उसका हम डैगर ले रहे हो तो ये इस तरीके से भी किया जा सकता है कि हम पहले उसका डैगर ले लें और फिर हम उसकी पावर एन ले लें। तो दोनों सूरतों में, यानी कि या पहले पावर ले लें और फिर बाद में डैगर लें, या पहले हम डैगर ले लें और बाद में पावर लें। तो ये दोनों चीजें क्या हैं? इंटरचेंजेबल है। तो इनमें हम देख सकते हैं कि ये जो सूरत हाल है वो इस तरीके से हो सकती है। ठीक है ना? अच्छा, फिर इस तरीके से अगर हम हमारे पास एडिशन हो मुख्तलिफ ऑपरेटर्स की, ठीक है, मुख्तलिफ ऑपरेटर्स ऐड हो रहे हैं, ए बी सी डी ऑपरेटर्स अगर ऐड हो रहे हो तो फिर क्या होगा? फिर हमारे पास ये होगा कि इनको हम इंडिविजुअली भी इनका डैगर ले सकते हैं। यानी कि अगर आप ये देखें कि ए बी सी और डी इनके डैगर्स हैं तो हम ए डैगर अलग ले लें, बी अलग ले लें, सी अलग ले लें एंड डी अलग ले लें और इन तमाम के डैगर्स को ऐड कर दें तो हमारे पास टोटल इनका आ जाएगा। एंड देन if you have the multiple of A, B, C and D and the whole dagger, the last term will then become first and then the second last, then the third last and then the first term. So D dagger, C dagger, B dagger, A dagger. मल्टीप्लीकेशन के अंदर हमारे पास जो इनका ऑर्डर है वो आफ्टर मल्टीप्लीकेशन रिवर्स हो जाएगा। ये आपने याद रखना है। कभी भी ये नहीं होगा कि ए बी सी डी होल डैगर इज इक्वल टू ए डैगर, बी डैगर, सी डैगर एंड डी डैगर, ऐसा नहीं होने वाला, बल्कि इनकी जो ऑर्डर है वो चेंज हो जाएगा, रिवर्स हो जाएगा। ये आप लोगों ने ख्याल रखना। मल्टीप्लीकेशन में, एडिशन में इससे कोई फर्क नहीं पड़ता। So these were few properties of the Hermitian adjoints. Now we are going to define the Hermitian and skew Hermitian operators, which are much important. We will use them again and again in future. Hermitian operators are those operators in which Hermitian adjoint of an operator is equal to the operator itself. That is called a Hermitian operator. वो ऑपरेटर जिनमें हर्मिशियन एडजॉइंट हर्मिशियन एडजॉइंट ऑफ ऑपरेटर ऑपरेटर इटसेल्फ के इक्वल आ जाए उसको हम कहते हैं हर्मिशियन ऑपरेटर। अगर हमारे पास ए ऑपरेटर है एंड ए डैगर ऑफ द ऑपरेटर इज इक्वल टू ए इटसेल्फ, दिस इज कॉल्ड हर्मिशियन ऑपरेटर। And this is why, this is because there is something inside this operator real, because the complex conjugate of a real quantity is equal to the quantity itself. When we take the complex conjugate of, let's say, 5, it will be equal to 5. Simple. So the Hermitian operator, keep in mind always, the Hermitian operators have real eigenvalues. For example, total energy operator, Hamiltonian, have the real eigenvalue. Energy value, total energy value is the real, because that has a physical meaning. That is why Hermitian operators are always those operators in which eigenvalues are real values, because when we take their Hermitian adjoint, they will give the value itself. It means they have the real values inside. So a dagger is equal to a. Whenever a dagger Hermitian adjoint of an operator is equal to operator itself, it will be a Hermitian operator, and it will always have the real eigenvalue. So whenever we take its complex conjugate of the average value, it will give you again same value without complex conjugate. That is the definition of Hermitian operator. And Hermitian operator always gives the real eigenvalue. There are skew Hermitian or anti-Hermitian operators in which the value of the Hermitian adjoint of an operator is equal to the negative value of that operator. B dagger is equal to minus B. This is called skew Hermitian or anti-Hermitian. And similarly, the complex value of that average value of that operator is equal to negative of the average value of that operator. So Hermitian and skew Hermitian or anti-Hermitian operator, you must know about these. And from here, anti-Hermitian operator means they have complex eigenvalues. That is why this negative sign comes. Whenever you take the complex conjugate of iota, this is equal to minus iota. So this minus with the operator is due to the complex nature of the skew Hermitian operator, anti-Hermitian operator. That is we call it anti-Hermitian, because the negative sign come with this. So this is the actually anti-Hermitian or skew Hermitian of an operator system. And the last type of the operator is the projection operator. Projection operator are basically Hermitian operators, but they have a further a condition with them. For example, a P operator is called projection operator if it is Hermitian, means the dagger of this operator is equal to the operator itself, and the further condition is that the square of the operator is also equal to the operator itself. There are two conditions for the projection operator. One thing is that it must be Hermitian, and the other condition is that the square of the operator is equal to the operator itself. That is called a projection operator. And it must satisfy these two conditions which I have highlighted in the text, that it must be Hermitian by this condition, and the square of the operator is equal to operator itself. For example, you have identity operator. Square of identity operator is equal to identity, because its eigenvalue is 1, and 1 square is equal to 1, and the complex conjugate of this operator, Hermitian adjoint of this operator, is equal to the operator itself. So this satisfied the both of the conditions for the projection operator. So identity operator is the projection operator. There are many other operators which are the projection operators, and they have their own consequences in quantum mechanics. There are a few properties of the projection operators. P1, P2, if you have a two projection operator and they are multiplied by each other, and we take the Hermitian adjoint, then I have told you that in multiplication the sequence will change. That P2 will come first and then P1. P2 dagger P1 equal to, now both of these are Hermitian, so P2 dagger will be equal to P2 and P1 dagger will be equal to P1. So this is equal to P2 P1, and P2 P1 is always equal to P1 P2. So P1 P2 dagger is equal to P1 P2, and if we take their square, P1 and P2 whole square, this is equal to P1 P2 P1 P2 multiplied, and you know P1 multiplied by P1 equal to P1 square, and P2 multiplied by P2, this is P2 square. And now if two commuting projector operators P1 and P2 is also a projection, the product of the two projection operators is always a projection operator. So now P1 is a projection operator, so P1 square is equal to P1 according to the definition of the projection operator. And P2 is also a projection operator, so P2 square will be equal to P2 according to the definition of projection operator. So P1 square is equal to P1 and P2 square is equal to P2. So P1 P2 square P1 P2 square is equal to P1 P2, and P1 P2 dagger is equal to P1 P2. So if you have two operators, projection operators P1 and P2, then their product is also a projection operator. This is the result. And sum of the two projection operators is not generally a projection operator. Sum is not in general a projection operator. And this was all about the different, properties of the operators. In the next lecture, we will start commutation algebra. Now, if you have any questions about operators, you may write the question in the chat box. And further, if you have questions after the lecture, while reading the lecture, you may send me an audio message on the WhatsApp group. I will also share this lecture on the YouTube channel and will send you a link on the WhatsApp and the WhatsApp group. I will send you the link. You may write your questions in the chat box. If you have any question, please, frankly, you can write it on the chat box. Okay. Hermitian and skew Hermitian के बारे में क्वेश्चन पूछा है आपने. Hermitian operator is that operator in which Hermitian adjoint of the operator is equal to operator itself. A dagger is equal to A itself. That is a Hermitian operator, and it has always real eigenvalue. And skew Hermitian operator is that operator in which Hermitian adjoint of the operator is equal to the negative value of that operator. That is skew Hermitian operators. Any more question? Okay, no question. Now you may further ask questions on the WhatsApp group. I will upload this lecture on the YouTube channel and will send you the link again. If you have more questions, you may ask tomorrow about the operators. Thank you very much.